Good afternoon, one and all. I am pleased to introduce Dr. Carlos Lopez-Martinez, a distinguished figure in the fields of electrical engineering and remote sensing. Dr. Carlos is an accomplished individual who has dedicated his career to the field of electrical engineering and remote sensing. He holds a master's degree and a PhD from Technical University of Catalonia, Barcelona, Spain. In addition, he furthered his expertise with a postgraduate diploma in data science and big data from University of Barcelona. Currently serving as an associate professor at Technical University of Catalonia, professional journey has spanned international borders. With significant experience at renowned institutions such as DLR in Germany, the University of Rennes in France, and as a group leader of the Remote Sensing and Natural Resource Modeling team at the Luxembourg Institute of Science and Technology, he brings a wealth of global insight to his work. His research interests are diverse and cutting edge, encompassing areas such as synthetic aperture radar theory, radar polarimetry, multidimensional SAR, and advanced digital signal processing. Dr. Carlos has authored over 200 articles in prestigious journals, books, and conference proceedings, showcasing his commitment to advancing knowledge in his field. Notably, he has received several accolades, including the USAR 2002 Conference Student Prize Paper Award and IEEE GRSS 2013 Gold Early Career Award. Despite his impressive achievements, Dr. Carlos remained deeply innovative in academia, offering his expertise in teaching at various levels from bachelor to PhD programs. Beyond his academic endeavors, Dr. Carlos has actively contributed to space missions such as Spanish BAS, Europe Space Agency's SAOCOM CS, demonstrating his commitment to real-world applications of his research. He also holds key roles in professional societies, serving as an associate director, editor for the IEEE GRSS Journal and MDPI Remote Sensing. Dr. Carlos brings a wealth of international expertise and a genuine passion for the practical implication of his research. Now let's warmly welcome Dr. Carlos Lopez-Martinez to the stage, anticipating the valuable insight he's here to share with us today.
So thank you very much for this kind introduction. Before to start, I would like to thank you, the Bangalore GRSS chapter, for this kind invitation. And especially I would like to thank Jaya for all the preparations that have made possible this talk and the conference that will start tomorrow. So this presentation is going to be or belongs to the Distinguished Lecturer Program, which is an initiative of GRSS where experts in different topics in the remote sensing community can bring the expertise to other people. So I'm glad to share with you what I have, some of the aspects I've been working on during the last year, so that are covered in this presentation. So basically, the presentation is going to be from SAR, Synthetic Aperture Radar. I'll go to polarimetry. I will present some concepts of polarimetry, then multitemporal SAR, and then how all this can be combined with a bit of artificial intelligence. Of course, nowadays we all put some artificial intelligence on the game because it's the only way to exploit the huge amount of data we have. So for instance, imagine that a European Space Agency is producing more than 20 terabytes per day. So I mean, you can scale the numbers and you can see the need of these tools. Okay. So here you have my contact information. So if anyone wants to contact for any kind of topic, so here you have my email, you have my LinkedIn account, so you can contact whatever. I mean, take all any means that you want to contact with me. Okay, I'm open to collaborate or to work or even to provide answers to your questions. So, which is going to be the principles of this lecture. So first of all, I will introduce the basics of SAR, of synthetic aperture radar, because I think they are necessary to understand later on what is polarimetry. Then I will come to introduce multitemporal polarimetric data, but basically how we can extract these two diversities in SAR to extract physical information. And finally, I will present some applications of multitemporal polarimetric data, and particularly I will focus on terrain classification. It's a way we can use multitemporal at the same time as polarimetric information. So the outline of this talk is going to be like this. First of all, synthetic aperture radar, just the principles, just to set the basis of what I'm going to present. Then what do I mean, or what do we mean by SAR polarimetry, how we can use it, which is the physical information we can extract. Then I will go to multitemporal SAR, what type of information we have, and finally, one application or using machine learning techniques, and in particular, as I said, the use of Sentinel-1 images, especially intensity, polarimetric, polarization, and interferometric coherence for classification, terrain classification. So, first of all, when we talk about SAR, the most important property of a synthetic aperture radar is that we can get multidimensional data. We can measure the same area in many different ways. So, if we have one channel, we have the classical synthetic aperture radar. If we take two images with a certain spatial baseline and sometimes with a temporal baseline, we go to SAR interferometry, and therefore we obtain information about the topography of the terrain. We can also see the movements of the terrain using multiple times this interferometric approach in the case of differential SAR interferometry. And the focus of this presentation is going to be SAR polarimetry. So in this case, we can have 3 or 4 images, and the particularity of SAR polarimetry is that we can have a very good geometric characterization of the target, and this is what I will show later on, and sometimes also a very good characterization of the soil moisture. I'm not going to enter into that topic, okay, but polarimetry is also something we can use to get an accurate measure or estimation of the soil moisture. We can even complicate even more. We can combine polarimetry with interferometry. In polarimetric SAR interferometry, we have 6, 8 images. In that case, what we are able is to explore the vertical distribution of targets, so we are able to study forests or glaciers or ice areas. We can even increase that approach in tomography, so we can have even large resolution in height, and also multitemporal. In that case, we can have ideally infinite number of images. We have the system repeating the same measure over and over the same area. So the most important property is that we can be sensitive to the dynamics of the terrain. And in the frame of the climate change, from my point of view, this is the most important characteristic of SAR. It's the best machine to obtain reliable multitemporal series because it's not affected by clouds, it's not affected by the day or the night, so it's the most powerful machine to obtain temporal data. Finally, and this is going to be something that is going to exploit in the future, is multi-frequency. We can have different systems. For instance, the European Space Agency has on the space already Sentinel-1, a C-band SAR system. In the future, they will launch RAUSEL, which is an L-band system. Our colleagues in the US, they are going to launch about next year NISAR, which is also an L-band system. ESA is going to launch about next year also BIOMASS, which is a P-band system. So all in all, we can combine all of them to get more information, okay? So in this lecture, I'm going to focus on SAR, on polarimetry, and multitemporal. From a mathematical point of view, all these different types of diversities can be treated in the same way. The difference comes on the information, on the physical information we can extract in each case. So I'm going to focus on polarimetry and on multitemporal. So let's go first to synthetic aperture radar, just to set the basis of this lecture. So what is a synthetic aperture radar? A synthetic aperture radar is nothing more than a radar. So it's a clock at the end. I have a transmitter, I have a circulator, I transmit one signal, the signal hits the target changes the properties of this echo goes back to the system, it is received, so therefore what I want to make is to invert this relation between the pulses so I can infer some property of the target. First of all, if I measure the time this echo travels from the radar to the target and back, I can infer the position. If I measure the Doppler frequency, I can measure the speed. If I measure how the pulse is changed, I can obtain more information. If, as we will see, the target can change the polarization of the wave. So from the change of polarizations, I can infer the properties of the targets. And this is the secret of SAR polarimetry. The target changes the polarization of the wave, so from this change, I can extract information. Okay? So, basically, a radar system is a side-looking system. So I have my sensor, which has an antenna. Okay? What is the problem? If I want to have a large resolution in azimuth, either I have a large, very physical large antenna, very few kilometers. This is impossible to put in a satellite. So what we can make, I can make an artificial long antenna by recording the echoes at different positions. So I can synthesize a very large antenna. And this is the origin of the name. It's synthetic aperture radar because I synthesize a large antenna through the recording the different echoes on the space. Okay? It's a side-looking geometry, so the geometry is a bit particular. It's not like optical systems which look into the nadir, so there is some distortions. It's a two-dimensional image. We have azimuth and range. We have different imaging modes. I will focus specifically on strip match, which is the classical, but basically we can have different modes compromising swath and resolution. So we can have modes with a very wide swath, with some relatively good resolution. I can increase a lot the resolution, so therefore the swath is smaller. The problem always is the same. If I increase the swath with a very high resolution, I need to handle with a lot of information. And sometimes the bottleneck at the end is the downlink of the satellite, because you cannot accommodate all the information on the downlink. And the most important property is that SAR images are complex. Every pixel for a single SAR image has an amplitude and a phase, because the process to construct this synthetic aperture needs to acquire the E and Q channels on reception. Okay? So therefore, images are complex, differently from optical systems, because the optical systems only measure the radiance, a kind of power. So here we measure amplitude and phase. And this is one of the most difficult properties of the system to handle the data, because you have to handle with the speckle noise, you have to handle with the physics, and the images, the SAR images, they don't look really nice to the eye, okay? Despite the kind of information we can derive is very useful. So, how does it work, a system? The SAR, the most important thing for a SAR is the spatial resolution. How do we achieve resolution in the range, okay, which is the dimension joining the radar with the target. So in here, okay, the resolution is obtained as in a classical radar. So basically, depends on the bandwidth. The larger the bandwidth, the bigger the spatial resolution. What is the problem? That legally we cannot transmit as much bandwidth as we want, okay? There are regulations, but nowadays, for instance, at X-band, the systems like the TerraSAR-X, it's able to transmit 300 megahertz, so you can obtain resolutions in the order of 1 meter or even below, okay? But what happens in the azimuth? In the azimuth, the native resolution is the one determined by the physical antenna, okay? So, going to the theory of antennas, okay, the larger, the bigger the antenna, the narrower the radiation diagram, and therefore the higher the azimuth resolution, the capability to detect targets at different azimuth positions. So, with an antenna of 10 meters, your space resolution is in the order of kilometers, which is not useful. So, how can I increase that resolution? Of course, making the antenna larger. So, first option, a very big antenna. This is not possible to put it into the space. For instance, perhaps the most important example is radio telescopes. I mean, all we know that these radio telescopes are 60 or even larger dishes. Why they are so big? Because they want to look at very tiny positions into the sky. So therefore, in order to gain resolution, I need very large antennas. So here is the same. How do I obtain a very large resolution? By having a large antenna. I cannot put a very large antenna. The second option is to make an array, is just to have a simple antenna and to copy many times. So the effect is the same, is to have a large antenna, but I cannot physically have multiple satellites, okay? This would be one way to make the synthetic aperture. So the third option is just to have one satellite that travels. So therefore, what I make, I record the echoes at each position, and at the end, I combine all of them to synthesize a large antenna. So that's why, at the end, I get this high resolution. So for systems normally, for the classical approach, the resolution we can obtain in azimuth is about on the order of the dimensions of the antenna, okay, in azimuth. Normally in systems like Sentinel-1 or TerraSAR or all these kind of systems, we have an antenna in the azimuth direction of about 10 meters. So therefore, the resolution you obtain with those systems is in the order of meters. So, which is something really useful for Earth observation applications. Another important parameter, frequency. We can measure at different frequencies. So here what you see, okay, is the Amazonian forest. So at X-band, we don't have penetration into the canopy. So basically, I'm sensitive to the top of the canopy. Okay? So therefore, you see here that the image is more or less homogeneous. As I decrease the frequency, I increase the wavelength, so therefore my wave is starting to penetrate into the canopy. So what I obtain at C-band, I have some penetration. At L-band, I have a stronger penetration. So that's why I see difference between the fields. The most important thing, first of all, is that these three images are taken at the same time. What you see here is a rain cell. So at X-band, the raindrops are very similar to the wavelength. So therefore, what you see is that X-band, I don't see the through the rain. Nevertheless, if I decrease the frequency, I increase the wavelength, the rain becomes transparent. And this is what we see here. We see a bit of effect at C-band because this is a heavy rain, it's a heavy rainfall. And finally, at L-band, it is completely transparent. And this image shows that we are not affected by clouds or by meteorological effects. I mean, it's not 100%, but basically, in most of the cases, we can consider that the system or the data are not affected by these meteorological effects. So this is a very good advantage to obtain temporal series. Here is another result. This is the desert of Chuquicamata. It's in north of Chile. Basically, this is the deepest hole made by humans. It's a mine of 1 kilometer deep, open mine. Okay, so you have here all the details. This is an optical image taken for Google. And this is what you see from the radar. Okay? First of all, this image is taken at 11 o'clock at night. So, as it is a radar, it is an active system. I provide my own source of illumination. I don't depend on the day-night cycle. And also, you see here, okay, you see here perfectly the hole. And what you see here is that this side of the hole is changed, okay? And the other side is also changed. Okay, this is because we are looking in a side-looking geometry, so it induces some distortions. We can go even to now global applications. And nowadays, we are in the era of global applications. So here I show a particular example where we have made a mosaic on all the South American subcontinent. So what you can see, the details here, you can see the Amazonian forest. It is pretty clear. You have the Amazonian River. You have the Argentinian Pampa here. You have Buenos Aires, which is here. this is the Silver River going through Buenos Aires. You have all the Andes, so you can have applications, large-scale applications. So you can, the most important thing is that you can have even large-scale applications at very high resolution. So nowadays, it is possible to map with Sentinel-1 the entire wall as a resolution of 10 meters each 6 days. Now 12 days because Sentinel-1B doesn't work, okay? But you can map at this frequency the entire Earth. Okay, so what we have seen is that with SAR, I can obtain information, high resolution information about the Earth's surface. What I can do with polarimetry? What is polarimetry, first of all? So, a system transmits an electromagnetic field, okay? An electromagnetic field is nothing more than a vector, okay? It's a transverse electromagnetic wave, so it's simply a vector, okay? So, this vector can vary in time and space. And here what they show is an electromagnetic field with a component in X, component in Y, traveling in Z. So if I take this electromagnetic vector, it describes these red arrows. So this is the electromagnetic wave, how it varies in space and time. Okay? So now, if I take the tip of the electromagnetic field and I plot the figure described by the tip describes this kind of shape. And this is what we call polarization ellipse. So at the end, polarization is nothing more than a way to refer to the vector nature of electromagnetic fields. It's nothing more than that. Okay? What is the advantage? Is that this shape can take many shapes. So, first of all, what do we have? We can have horizontal polarizations. Our field only varies on the horizontal dimension. We have vertical too. Okay, so our field only varies on the vertical case. Okay? We can have also circular. Okay, we can have circular, left circular and right circular. Okay, we can have the both of them. Okay? And in the most general case, basically we have elliptical polarization states. So the idea is that my system will transmit a polarization, the target will change that polarization, so from the change of the polarization, I can extract some properties of the target. So the target induces a change on the polarization, so I can extract certain properties through this change. So this is basically the basis of SAR polarimetry. Okay, so how do I measure polarimetry? Remember, we have a radar, and now we have to play with two polarizations. So normally the systems work on linear polarization basis, horizontal, vertical. So a normal radar will transmit one polarization and will receive one polarization. What I can do? I can add a second receiver. And the second receiver can be tuned to the other polarization. So I transmit in one and I receive in two. Okay? And then I can have two images, two SAR images. Okay? In this particular case, is the mode of Sentinel-1. If someone of you have worked already with Sentinel-1, you work with BB, BH. So basically, we transmit in B and we receive in B and H. But polarization is something more. What if I can also transmit on the other one? So I transmit in horizontal, I transmit in I transmit in horizontal and I receive horizontal and vertical. Okay, so I get one column of this scattering matrix. What I can do is I can transmit on the other polarization, I can receive in the other two. So at the end, when I have my measure is a 2 by 2 matrix. So normally this matrix is 2 by 2, but only 3 elements are different because the HB and BH on most of the targets are equal. So therefore, for each pixel, we have no longer a complex image, but we have a complex matrix. Okay? And that's the advantage. We acquire more information of the same target. Okay? What is the problem? The problem is that the frequency at which I have to repeat these pulses needs to be doubled. The issue of this doubling the PREF is that the swath is half of it. Okay? That's the limitation polarimetry introduces on synthetic aperture radar. The swath is reduced a bit. Okay? It's a kind of compromise. So, what do we have? We have diversity. Okay? We have SAR images. In here, I plot some images taken by DLR on the north or on the south of Germany. I transmit in H, I receive in H. I transmit in B, I receive in H. I transmit in B, and I receive in B. Okay, that's my polarimetric wall. Okay? But there are much more information than that. And polarimetry, perhaps the most important polarimetric observable, are not just these images, but the correlation between them. And this is perhaps the most important polarimetric radar observable, is the correlation between the polarimetric channels. So as you can see here, if I make the correlation between HH and BB, it's also complex. As you can see, we have some information in amplitude and in phase. For HH, HB, we have less information. Okay? But perhaps the most important information at the end, finally, is this phase in here. SAR is able to measure that phase. In the case of interferometry, this phase has topographic information. In the case of polarimetry, this phase is sensitive to the geometry of the target. Okay? So let's go to combine the images. If we make the combinations, what we can see is the following. If I make this intensity HH plus BB square, whenever this term is high, I can assure that what I have is single bounce scattering, is a surface. If I make the difference, HH minus BB, whenever this term is high, I'm facing double bounce. So basically, I have this wave that hits the ground, hits one target, and goes back, and the same on the trees. So therefore, I'm sensitive to this double bounce. And whenever HB is high, it is related with volume scattering. So as you can see, polarimetry itself reveals information about the geometry of the target. Okay? So let's go to this example. This is the south of Madrid, the capital of Spain. So here is a SAR image in BB. No problem, I measure the intensity. So basically, what I measure in here is just this image. So what happens now if I combine these three images? Okay, not really these three images, but what if I combine this image with this, and we put one color to each channel? So basically, what polarimetry gives somehow to the synthetic aperture radar is it gives color to the image. Okay? So remember, if we put HH plus BB is proportional to a surface. So wherever it is blue, is surface scattering. Okay. Now let's go to green. Green is volume. So whenever it is green, it means that we have volume. In this case, this area corresponds to crops, and this area corresponds to forest. And whenever we have red, it's double bounce. So I don't see that if you see very well, but in here, you see a red line. Okay, so this red line is the double bounce of a power line. I mean, the electromagnetic field goes to the ground, bounces on the ground, goes to the cable, okay, and the transmittivity of the cable is very high. It goes back, so I'm able to see the power line. So here is another example. This is the Andes. This is the city of Santiago de Chile. So L-band, C-band. If I put polarimetry, I can give color to the image. So what I can see here, first of all, you can see that wherever is blue, it's a flat surface. So where do you see flat? In this lake in here, okay, and on the top of the mountains. These mountains surrounding Santiago de Chile are very high, so above a certain point, there is no more vegetation. So this is a flat. Below that point, you have vegetation. That's why you see in green, and that is revealed by polarization. If we look at the city of Santiago more properly, you see that in some areas you have red, which means perfect double bounce. So in that case, the streets are facing the trajectory of the radar. Whenever these streets are not facing perfectly, are not perfectly parallel to the trajectory of the radar, what I get is volume scattering. I get multiple bounces, and that's why on these urban areas I see in green. The way to resolve this duality is to combine polarimetry with interferometry. Okay, I can break this duality. Okay, so we have visited already two things: SAR, very high resolution; polarimetry, information about geometry. When I can get with multitemporal, I can get the dynamics of the terrain. So here I show some example. This is a temporal series of radar-sat-2 images, C-band, fully polarimetric. This is on the Netherlands. This is a quite old data set, but very useful. So remember, blue surface, green volume, red double bounce. So here what we have is from April 2009 to September. So basically it's the growing period of the crop area. So before the crops grow, what we see is surface. So then up from April more or less, the crops start to grow, so they start to reveal the volume. And at the end of the season, okay, what we have is going back again to surface. So we are sensitive to the dynamics. In this case, I have just shown the behavior of a crop area, okay? But you can be sensitive to the dynamics of any type of surface. So what do we need in the case of multitemporal? First of all, revisit time. We want to minimize it. We want as many images as possible, okay? Nowadays, this is difficult to obtain from the space, okay? And also, we want the length of the temporal series to be as long as possible. Of course, my desire would be to have a 30-year-long time series of daily images, okay? Therefore, you can be sensitive. You can be sensitive to all the dynamics, and therefore you can start to track, for instance, climate change effects, because you have a sufficient long record. Okay, so how do we minimize the revisit time? Just putting more satellites into the space. So this is the case of Sentinel-1. Okay, so so basically what I have is two satellites flying in counterphase. Okay, they are at quiet. So in this way, what I can obtain is, or I can cover the entire Earth every 6 days, which is quite a big achievement. Okay, there are other systems like SAOCOM, the Argentinian system. They are able to measure the surface every 8 days at L1. Okay, so how do I increase the revisit time? I start to put more satellites into the space. Okay, so I cannot do it with systems like Sentinel because they are super expensive, but this is what the private sector can make, and this is what we call new space. I mean, you have seen now many private companies all over the world launching constellations of satellites. So the objective of constellations is basically, first of all, to be able to command any image with a minimum latency, but also to have revisit times below the limit of 6 days. Okay? There are companies, ICE, Capella, in the SAR sector. All those are driven by the private sector, because the private sector, they don't use these big machines, they use small satellites. Okay? Of course, they are not as accurate as the big ones, but they have the advantage that they can obtain images in a very rapid way. Of course, with some limitations. Another way to increase the revisit time is to have ground systems, okay? So this is a system we have developed at UPC. It's a ground-based SAR system. Nowadays, it's able to operate at P, L, S, C, and X-band, okay? Both in polarimetric and interferometric modes. And the advantage is that we can take images very rapidly. Let me go back to this to explain the video. Sorry. So in this particular system, in this case, or the case I'm going to show you now, we were able to take one image every 8 minutes. But nowadays, we can take images even below a minute. Okay, we have improved the hardware. So this is what you basically obtain. Okay? Okay, perfect. So I'm going to, this is the system operating at all the frequencies. We have some corner reflectors to calibrate too. Okay? So we have measured this area in here, which is some forested area, which is very, very nice. So our radar is here, and we try to face this area in here, which basically you will see now, which is we are measuring this. So we have the trees, okay, and we know that below the trees we have rocks. And this is something we know. So this is what we see at X-band. You see that you see the movement because they are affected by the leaves, by the wind, etc. What happens if we start to decrease the frequency? We obtain an image which is less dynamic, okay? Now, what happens if we go to L1, the dynamics is even slower, okay, despite the resolutions are different, we cannot avoid that. And finally, if you go to P-band, you see that the area is super stable. Why this? Because the trees are transparent at this frequency. So what we are seeing is the terrain below the trees, and that target is completely stable. So that's what we see. Here, this detail in here belongs to a big rock behind the trees. So we are able to penetrate. I mean, this system is not intended for the same applications as the big satellite, of course. For instance, we have developed this system with a private company. They are intended for early warning system, for mining or for glaciers or for whatever, and also as a scientific instrument to develop models that therefore, that afterwards we can apply to satellite data. Okay? So if you have any question, I mean, raise your hand and I can answer the question, or afterwards. Okay, so where we are now. Synthetic aperture radar, I can obtain high spatial resolution. Polarimetry, I can obtain target geometry. Multitemporal, I can obtain dynamics. So what can I do with all these? Many applications. One of them is classification for Sentinel-1, or using Sentinel-1. So in this particular case, we are also, apart from using the polarimetric information, we are also using the interferometric coherence. I can calculate the coherence, as we did with polarimetry, but for images taken at different times. So therefore, the clue behind this approach is that I can have a better classification because the different targets behave dynamically different. So I can start to differentiate better through the temporal behavior. Okay? So here, for instance, this is Doñana wetlands. It's the largest wetlands in Europe, in south of Spain. So what do you see? You see the coherence, how it decreases with time. Okay? The larger the separation between the images, the lower the coherence, except for some targets like urban areas. As you can see here, this urban area doesn't change in time. So it's very stable. Nevertheless, Other areas like this rice or these wetlands, they are very dynamic, so I lose coherence. So apart from interferometry, for polarimetry, sorry, I can use interferometry. I can use the dynamics. So this is basically where I put my multitemporal information. In this particular case, what we did is we measured 3 areas, one in Poland, one in South Tyrol in Italy, and one in Spain. I will focus the results on Spain. So in here, we are taking 51 acquisitions, and we can create more than 1,000 interferons. So I can measure the temporal information in more than 1,000 different ways, because I can correlate all of them. So I have a very accurate temporal dynamics. We have used that information in a round-robin approach, comparing different approaches, all of them basically based on artificial intelligence or machine learning algorithms. So from there, maybe the most important thing is the following. Okay? These are the classification results for Doñana in Spain, for South Tyrol, and for Poland. I will focus on this. Okay, so first of all, what happens if I use intensities? Okay? The overall accuracy I obtain is 74 and 74 if I use one or the other polarization. If I use polarimetry, that is 2 images, I can increase my rate of classification. Remember, this is an overall classification accuracy. I'm not referring to a particular class. I will go to this topic later on. What happens if I use only the temporal information through coherence? If I use only coherence in one polarimetric channel or in the other, these are the results I obtain. And what if I combine this only temporal information with polarimetry? I can increase the rate of classification, which is almost 80%. I can do both. I can use polarimetry, I can use temporal at the same time. So as you can see, the combination of intensities and the combination of temporal information, that increase the overall accuracy. So increasing my diversity, I improve the rate of classification. Okay, but there are some questions here about how I obtain that rate of classification. I have given this classification accuracy as an overall accuracy. What happens for particular classes? Of course, I don't classify all the classes in the same way. Okay? Also, how the different informations I put into the classifier affect each class. I mean, for one class, maybe the classifier takes some inputs. Maybe for other classes, they take other information. And maybe the question, the most important question, okay, is how the temporal information is considered. And this is where we were interested when we did this work. Okay, this was done in the frame of an ISA project. How do we apply this? We use artificial intelligence approach, in this case a random forest machine learning approach, because it has the advantage that is self-explainable. I can obtain how much one input affects one class. So I can make that study to see how each input affects each class. Okay, so this is a situation we have. We have the data, and we have the ground truth. This was provided by the local producer because this is a very important region for rice production, so we got this map. Okay, so we can train, we have ground truth. What do we have? We have the data, we have 49 temporal samples for Sentinel-1. We have the ground truth, and which are the input features? We have the temporal information, the intensity, the coherence, and both polarimetric. So if I combine all these combinations, okay, all these parameters, with all the temporal, on all the acquisitions, I end up with more than 500 features. So the question here, of course, I obtain a very good classification, but the question here is that if all these 500 parameters were influencing the final result in the same way. especially in the temporal dimension. This was our question. Okay, so these are the classes we have. Okay, we have some artificial surfaces, we have some vegetated surfaces, some forests, some water surfaces, and here, as you can see, the number of pixels we have per class is not distributed evenly. So we have to put into the table mechanisms that are able to tackle this balance between the classes. So we did that, and we corrected that, so we can get results which are minimum. As you can see, 54% of the area are rice fields, because it's a rice production area. So we use random forest, which basically, a random forest is nothing more than the combination of the decision trees, random decision trees, okay? In this particular case, we have 400 trees. For every tree, we selected randomly 50 parameters. So the advantage is random trees nowadays, our experience is that very robust for synthetic aperture radar processing, okay? Typical, we train with 20%, we test with 80%, okay? We make this separation, which is classical in machine learning approaches. Okay? The advantage of random forest, as I explained before, is that I can give, or I can see, which is the importance of each variable on the final result, okay? So basically, I can give one importance to these 519 features, okay? This is how they are calculated, okay? First of all, if I look at how I classify each class, okay, I measure the precision on the terms of the F1 score, which basically is a combination of precision and recall. Precision is the current predictions over the predicted class, and recall is correct prediction over the original samples. So basically, it tells me how good, how bad I am in the classification of a class. So what you can observe is that for some classes, you are very good, for some classes, you are very bad. Okay? For some classes, you are close to 94 with 94%, and for other classes, you are very bad, okay, 67%. So the question is, we wanted to study how these parameters affected each class, okay? And the final question is I really needed this large amount of samples, if I needed 500 input parameters, because the way of thinking nowadays in the machine learning community is basically to use the idea of a black box. I have a network, can be very simple, can be deep learning, super deep with many neurons or whatever. So basically I throw all the data to the network, and I expect that the network will, with some kind of intelligence, will select the correct one, okay? So our idea is that this is not the most optimum way to do it. Okay, and we wanted to study this effect. So here, what I show is the importance of all the 500 variables. So as you can see, okay, there is a minimum amount of features that influence the most on the final classification result. Okay, and also here, what we wanted to see is where is the time. Here we don't have the time, okay? Are all the variables, all of them are temporal, but they are not giving explicitly the time. And we wanted to see how is the influence of time. So here is just an, okay, how is the plot? So the data is not ordered temporarily. We don't see the temporal patterns, by the way. So what we did is we worked too much, and what we did is to offer a new representation for the temporal information. So here, what I show here is, okay, this is the ratio of BBBH, the intensity, okay, in orange you have for one channel, for yellow you have for the second channel, and you have the coherences, okay, for 6 days, for 12 days, for 24, for 30, 36, 42. And the size of the dot gives the information of how important it is. So what can I observe here? I can see, first of all, that most of the information comes from very particular temporal points. Second, if I go to coherence, I can see here that whenever I have 6-day coherence, because in this period we didn't have the 6-day coherence because the system was, the Sentinel-1B was not launched, okay? So we had only 12-day coherence. So what we observed is the 6-day coherence is very important. Of course, we wanted to see this effect on all the classes. So we plotted this representation for all the classes. So what you can see is that for many classes, we don't know why, only certain times, certain temporal samples were giving most of the influence to the final ratio. And the most important thing is that those times, or those time points, were more or less the same in most of the classes. This is the rest of the classes. So here we saw this type of classes, which is, this is water bodies. So as you can see, the temporal samples that give most of the information for the classification are different, okay? So basically, we wanted to explore how this temporal information could be used, okay? So this is what we did in the following. So the important information we obtained from here is that, for instance, intensities give more information than coherences, okay? The quotient BH/BB is irrelevant in this particular application. So we can see that whenever we are on urban areas, BB is larger than BH, so we can use these channels of BB to study these areas, okay, because the importance of the double bounce scattering. Whenever we are facing volume, crops, or forest, BH is more important than BB, so in this case, this is because BH is sensitive to the volume scattering taken into the plant. So therefore, I can have sensitive to the different type of target. But what happens with the time? So, this is the test we did. We take a year, we limit our classification to 1 year of data, okay, and this is what we obtain. If I use all the samples, okay, all the temporal samples and all the information, that is 519 samples, my rate of classification, global classification, is almost 90%, so very good, at the cost of injecting 500 parameters. But what happens if I selectively take the 10 most important temporal samples? I reduce the number of input parameters to 70. So it's I take a little bit more than 10% of the original samples. My rate of classification only drops 3%. So that means that I don't need all the temporal samples, okay? And the most important, and for this we don't have an answer yet, is that instead of taking the 10 most important variable, I take 10 temporal samples randomly. So of course I will not select the optimum ones. But even in this case, when I select 10 of them randomly, my rate of classification is still above 80%. So our question is, to which we don't have answer, is what is the proper temporal sampling, okay, to obtain the best classification accuracy with the limitation selecting only a certain part of the temporal area. So it means that we don't have to indiscriminately feed the network with all the temporal data. We can select a very reduced set of these temporal samples, okay, to obtain a classification rate that is still very good, okay? So therefore, the temporal samples can be reduced by 80%, and this is very important, okay, for classification. I don't need really images every 6 days, okay? But the classification, okay, only drops 3%. So how to select that is still an open question for us, okay? So therefore, we save a lot of power and a lot of storage. And nowadays, most of the, one of the most important problems of these artificial intelligence algorithms is that they are really intensive in terms of power consumption, especially in training, okay? So if we use optimum ways to reduce this power, okay, I save power, or I can use all this computational power that I need to classify input parameters which are not important into other processing capabilities that could improve my classification. Just to close, okay, which are the basic information I think, which is the take-home message. First of all, SAR systems allow to obtain Earth information with a very high spatial resolution, okay, in the microwave electromagnetic part of the spectra, so therefore they are complementary to optical systems. They are not competitors, they are complementary. And the most important thing is that the acquisition is independent of the weather condition and the day-night cycle, okay? Polarimetric SAR data are sensitive to the geometric properties, as I said before, also to the dielectric properties, and also to the soil moisture at the end. This is a sensitivity I have not analyzed in this lecture, okay? Multitemporal data are sensitive to the changes, to the dynamics of the target. That's why at the end we want as many temporal samples as possible, because I can resolve temporal processes, okay? Maybe some temporal processes are super fast, so I need super, the revisit time has to be very short. For instance, if we think about early warning systems, I don't know, to landslide, to say something, I need, of course, to minimize the revisit time in order to be or to emit an alert as soon as possible, okay? And finally, artificial intelligence must not be applied blindly to multidimensional SAR data, okay? There are intelligent ways to apply all these techniques, okay? So with this, I will close my lecture, so I'm now open for questions. Thank you very much.
Thanks for a beautiful lecture, actually.
Thank you.
I love the experiment design, what you had in the last one. My question is very fundamental to understand. All of this is based on the angle, right? And we already have this the capture happens at a side-looking angle.
Yeah.
And we're talking about the return coming either in vertical or horizontal. So I'm interested in understanding how much of that error creeps into your observations, so that what we're observing is not really orthogonal, right?
Of course, I mean, it's affecting. I mean, the type of target you see with one angle, okay, is different from the same target seen from a different, for a different angle. So of course, I haven't mentioned here, but whenever whenever we work with synthetic aperture radar, we must pay attention to the incidence angle. So nowadays, the classical way of the approach is to always look at the same incidence angle, okay? Because, I mean, you eliminate this dependency, this uncertainty, or you reduce it to zero because you have only one incidence angle. The other way is to try to explore these machine learning approaches which are able to tackle with these different incidence angles. So at the moment, we haven't worked too much on that. But of course, incidence angle could be another type of diversity, okay? It would be the problem is that you cannot control it. It is commanded by the system from the geometric acquisition of the images.
And similarly, you said even wind may affect that response, meaning the observation. So how do you accommodate for all of these when you model?
I mean, whenever you analyze intensities, that's not pretty much a problem. No, it's whenever you start to talk or to analyze interferometric coherence is therefore whenever you have to take into account the decorrelation. And this is a very standard way to do it through what is called the temporal decorrelation. Basically, there is a physical model in which you can split coherence in different terms. Polarimetric, SNR, one of them is temporal. Of course, if the wind is too much, the temporal decorrelation will be 0 and it will cancel all the decorrelation, so you won't have information. And basically, the radar, you are sensitive to the targets which are in the dimension of the wavelength. So at X-band, you are 3 centimeters, so leaves are more or less that size. So the wind affects that, okay? So we hope that, for instance, with P-band, which is 3 meters, you don't see the leaves, you almost don't see the branches, you only see the trunk, so you expect to keep stronger coherence. But the target you are looking at is different, because at P-band you see the trunk, at X-band you see the canopy. They are completely different.
Thank you.
You're welcome. The? This where?
So it is a pulsed radar system that you are using?
Sorry?
Pulsed radar system?
No, it's a FMCW. Yeah, because you need a lot of energy to get SNR.
So what is the resolution in various bands?
In range is about few meters, I mean. Depends with the frequency. Okay, at X-band is 1 meter, at P-band is kind of 20 meters, and in range they are more or less the same because we are using, if I'm not wrong, about 200 megahertz. So it's in the order of 1-2 meters. Okay,
So basically, the specifications of your experiments are available in open source, or it's a?
Yeah. It's I mean, it goes to the company. Yeah? There is a company behind, but we have publications, so you can. I can give you the reference of the publication so you can have the details of the system there, okay? Basically, the system was done by one of my PhD students, so the PhD is available except one chapter, which is under embargo at the moment because there is a company behind, but you can have all the details. No, they are open.
So
or you can contact my friend.
It's a SAR system mounted on a linear array?
Yeah, it's mounted in a linear array, which is 2 meter long. Okay. Now we are operating. This was the first version. We are operating a second version, which is lighter, faster, and more. It's a system with, the goal is to commercialize the system. Okay, so we have to simplify somehow.
What about the scope of this feature learning? Because in the experimentation you mentioned that the number of features are reduced, the accuracy drops only by 3%. So what would be the scope of feature learning with respect to not losing the classification accuracy?
Yeah, this
for further research, I am asking.
At the moment is just to try to learn how temporal affects the classification. At the end, in this particular case, we focus on classifications, but we would like to have a more fundamental question, is how to deal with temporal information in the machine learning environment, just to avoid to throw it blindly all the data. I mean, this fundamental question is how a neural network takes temporal information. We are exploring other alternatives because you have these new, how they call them, these temporal neural networks, these long-term
temporal neural networks,
long-term, short-term memories and this kind of stuff. So we are exploring those ideas at the moment.
One more connected question. Is this feature learning always connected to the type of target you are detecting?
It depends on the target.
Target.
So it's something more additional you have to add to this, to that. So the problem is a very highly multidimensional problem. So we wanted just to give some physics to what these machine learning algorithms or deep learning algorithms are learning.
Okay, I am working in that, so I would like to. Thank you. Thank you.
You're welcome.
Hello, sir. Thank you again for taking your time and flying to India, and hope you enjoy the conference.
Pleasure.
So I come from the industry, so we are a startup. We use SAR data to monitor pipeline right of way. And right now we are just stepping our toes into the polarimetry analysis of SAR data. So we use S1 data to monitor changes on the pipeline right of way. Then we task like Capella, ISI, or Umbra to fly the satellites through those detected changes. So right now we want to get into classifying like those high resolution SAR data, since they just scan in single polarimetry. So we want to classify. So we wanted to advise, should we go just with the amplitude-based classification, or should we move to polarimetry? I don't know if polarimetry is possible with a single band.
Well, that depends on if your system has polarimetry, go to polarimetry. If your system doesn't have polarimetry, don't use polarimetry. You are not able. But I would recommend that you have to test it to see what you obtain. But for when you go to high resolution, polarimetry is very tricky. Yeah, because in here, what I have shown is results what we call distributed targets. I mean, the target is larger than the resolution. When you increase resolution, the interpretation of the polarimetry takes a different role because everything is a point target. So therefore, you don't have a speckle, you have to interpret it differently. So you have just to try, okay?
And how do we do the machine learning? Because these satellites go at different angles. They look from different places as their capacities available.
I don't know. I would start as I did here. You throw everything to the network and you start to study the classification results. And the most important thing is to establish ways in which you can relate the output with the input. That's the main issue of this neural network. They are not explainable. So maybe you could use some of these new approaches based on physically aware or physically explainable AI or this kind of thing. I'm not expert on that, okay? But this is something you could try.
And the final question, should they be of the same sensor or can I do different?
Sorry, repeat?
Do we have to be from the same sensor company or we can throw different sensor companies?
I mean, just try.
And even generations, because there are multiple generations. Older generations don't give that good results. The newer ones, maybe INSAR capable.
You just try. I mean, the problem is that everything will depend on your final application. I can tell you here some recipe that it may work for my application, but it may not work for yours, which are very particular. Maybe you don't find papers dealing with your application, so you have to try it with yourself. You have to make research. Okay?
Thank you.
Welcome.
Hello, sir. I have few questions. The first one is I'm a little bit curious about how to create a ground truth, because we are handling a lot of temporal resolution, and from which time period we have to take it. And if we are taking for a once period, is it applicable for the next? When site also may different, location will be different.
That's the $1 million question.
So we have to manually label it. That is the only way to do, or?
My first answer is the $1 million question. It's super expensive, we know. I mean, at PolSAR conference is a recurring question, ground truth. But nowadays there is an alternative, which is to use generative artificial intelligence. You can use all those techniques. You can synthesize SAR images according to given statistics. So that's something we are exploring.
But when we are dealing with level 3 classifications, so we have to deal with different kinds of classes. So it's auto generation of ground truth. Is it reliable or not? So that will be one research. And one more query is that is there any open source software available to work on? Because I heard about Snap will work, but there are a lot of limitations with the space constraints.
You have PolSAR Pro. Which is the standard of ISA for polarimetric processing. At the moment, I know that they are trying to switch to Python. So slowly they are going to Python. But you can look on the internet. It's Professor Eric Poitier in Rennes, France. So you can download. Everything is open source. It's in C, on C. It's ANSI. It's super standard.
Yeah.
Okay, and absolutely all the algorithms on polarimetry are in there. Everything is in there.
I'll look into
and it's more than 15 years old.
Thank you.
So you have calibration, you have classification, you have decompositions, speckle. You have even a simulator for forest.
Okay.
The PolSim. Yeah. You can simulate, I mean, a very short, very simple classification, but can be useful for forestry applications.
Okay. Thank you. Thank you so much.
Welcome. And there are other softwares, especially in the interferometric community, you have more options.
Thank you.
So one question she already asked about labeling the data set. So how to create, do you have any link where some sample images with their labels are available for training model? Because some people are not from remote sensing background, but they are from machine learning background. So they may not know much.
I know that in the optical community, they have already some million images, small images. Maybe you could use that. If they keep the geometric coordinates of the areas, maybe you can translate that to SAR or something like that. But it's a very difficult problem. In that case, what we have is that the local producers of rice in Spain, they had a very high resolution land classes that they keep or improve each year. So we were having that for that particular region. So in there we train rice detection. Now I could bring my model to the rice in India or in China. The problem is it doesn't work because practices are different, rice is different. So the translation problem is still open. So ground truth is something, is one of the bottlenecks of remote sensing nowadays for physical application.
And what about some distortion like interference or phase estimation, error correction? Where are the resources for knowing how to, because one of my students working on this phase estimation or phase correction in the SAR data for object detection and classification kind of a problem.
What type of errors do you mean?
This by phase unwrapping algorithms applications in SAR data.
In that case, if we talk specifically about interferometry phase unwrapping, the main source of error at the end is the coherence itself, because as you go to lower coherencies, your phase is the quality is very low. So one alternative is just to use improved speckle filters that could estimate better the phase, and you could have a better unwrapping maybe.
Okay.
Yeah, I would start to that. There is this local approaches. They are super heavy computationally. They are super heavy, but you obtain very good results.
Okay. Thank you.
Yeah, the problem is when you have one target in your resolution cell, the problem is totally deterministic. Perfect, I mean, I get the sigma 0, I can invert, I can get the properties of my target. For instance, if you have a corner reflector, from the radar cross-section you can get the dimensions, no problem. If I go to a mild resolution like Sentinel-1, you have fully developed speckle. In this particular case, it's very perfect, I can average, I can obtain the polarimetry. The problem is that whenever you don't have one, and you don't have infinite, that's the worst case, because there is not even analytical solution for that. So this is also a problem in the laser community. So the high resolution, the problem is that you cannot assume fully developed speckles, so therefore the physical interpretation of the information is not deterministic, but also is not totally random. So that's the problem there for the interpretation of this data.
Basically, you mean to say the traditional decomposition algorithms
do not work there. No. You have the target decomposition theorems for the scattering matrix. So there's for point targets, everything works. I can obtain the information. You can have the classical decomposition theorems for the C or T matrix that work on the other extreme. In the middle, there are some issues to interpret those decompositions. Okay? Because there is not even, as far as I know, for more than 3 targets into the resolution cell, there is no analytical solution of the field. So therefore, you cannot interpret physically what is inside, but also you cannot go to a statistical description because you don't have the proper analysis. Maybe some of the works that go into that direction is the work of our colleague Alejandro, who is trying to study advanced statistics, okay, for mainly urban areas where you have something which is not Gaussian, something which is not deterministic. The problem of those things is normally that this characterization is based on higher order statistical moments. In order to have a reliable estimation of that statistical moments, you need large windows, and normally you don't have the luxury to average so many pixels, so therefore you have to. No, I'm not saying that it's impossible. I never say that. I mean, I think.
Averaging will, I don't know, I mean, this averaging, ensemble averaging will totally change.
Yeah, exactly, and maybe you don't have enough samples to have a reduced uncertainty. That's the main issue. Huh? You can go, in that case, my recommendation would go to higher order statistical moments or to these advanced statistics that could somehow explain the distribution of that. But they are super heavy PDFs. Huh? It can be done, it can be done, but it's super heavy.
When you generate a series of sentinel scans, do you use some kind of a temporal speckle filter?
No, I simply use PolSAR at the end.
Okay.
Yeah, I did my PhD on speckle, but at the end, it doesn't play much role. Okay. Of course, once you define your application, you make your study, you can use super advanced speckle filters. The problem always is that the speckle filter, I mean, SAR images are super huge, 30,000 for 50,000. I want to have the image filtered before my retirement, okay? That's a problem, okay? They are super heavy. They are very good, but they are super heavy computationally.
Thanks.
I have one quick question on, so these sensors are degrading, right, over
Sorry,
time.
repeat again?
So these sensors are degrading over time.
Yeah.
So the signal we receive is a inferior signal than last year, than previous year, than previous year. So when we deploy these sort of models in production, meaning they're actually working, finding the LULC classes and whatnot, how do you cater to this? Because we don't know how they're degrading.
This is not totally true. They are not degraded. Depending how you use, you start to see the seasonal effects. The coherence can even grow. So the problem is that up to the moment, as far as I know, there is no deep study of the dynamics you can observe with SAR. This is still an open question. From my point of view, it's still very open. The only temporal models I know is the temporal decorrelation model. There are some that basically you assume that the correlation decreases exponentially, as everything in nature. You assume that. Somehow it fits. We have tested with L-band for SAOCOM, more or less fits. For C-band also more or less it works. Okay, it's not the perfect model, but it fits almost everywhere.
Because what we have observed is, like, let's say if we are observing the built-up areas, which are supposed to give you similar signature throughout the year. We studied subsequent years, and the signatures have started to look different. So one of the interpretation is probably the actual sort of electronics on the actual sensor is degrading, which is why the signals we receive are very different.
Yeah, because imagine that, I don't know, I have a system that measures the street in front of the institute. One day you have some cars, the day afterwards you have the other cars, you have more things, few things. So all those changes affect the signal. And as I said before, the combination of all these signals is not deterministic, but is also not random, so I cannot average. So it's something in the middle. So that's what creates a lot of problems with urban areas. So that's why normally one of the reasons to go in urban areas to high resolution is precisely to try to reduce this effect. The only problem is that to have that data is very difficult.
And expensive.
And very expensive. It's 6,000 euros per image. This is what I pay. I have paid for that. Huh? So no, it's not. I mean, it's not. That's not a business model that works. That's my impression.
So thanks for sharing the knowledge. It was very insightful. So my question is, so if in case I have to build a solution, I always go for optical data. But from your expertise, I just want to know SAR data wherever it can excel, and also I want to know if you want to build solution for this, you don't use SAR data. So based on your expertise, I just want to know like where SAR data are really good and SAR data cannot perform good. A broader one.
I didn't understand your question.
Okay, so I want to know, for example, if I want to build a solution for a particular application, for these solutions, don't go for SAR data. In this area, SAR data doesn't excel well. In this SAR data, SAR data can excel really good. So can you just give a broader opinion on SAR data from your expertise?
From resolution, you mean?
Not just resolution. Resolution, if I want to compare Sentinel-2 and Sentinel-1, it's almost 10 meters, right? So you said about machine learning, you can do classification, agriculture, those things and all. So even with optical, we can do the same. So just want to know, can SAR data do better classification than optical for input?
No, I think that's a wrong question, because that depends on your final application. For instance,
yeah, that's what I'm asking. For what applications can we build?
So whenever you are interested into the geometry of the target, on the water content, the soil moisture, or whenever you want to study volumetric targets, no doubt, go to SAR, because optical doesn't have that type of sensitivity. Okay? Whenever you want to go to some material properties, the health of the plants, the color, then go to optical. That depends on that depends on your application. That depends on your application. If you want to go mainly for geometry, volumes, the only way is to go to SAR.
Thank you.
Okay.
Thank you very much for this interesting presentation. Related to this question, actually, because this is a classification that you have done, right? So to stay in the topic of the optical and the radar data, so if you look at you would do the exercise, let's say, with the optical data or a combination of both, do you have any idea how is it like if you put the radar, it's like, say, a 30% increasing accuracy, or I don't know if
we
you've
have
done
done, in the frame of this SAR project I mentioned, we made even the combination with optical, and optical can get very good classification, but if you combine both, you can improve your classification. What is the problem? If I make classification in Europe, optical data is perfect. There are no clouds. In the tropics, the problem is that 70% of the time, you have clouds, so you can end up with terabytes of clouds. So in that particular application, in that particular area, there is no other way to go but SAR. That depends. Always depends on your application. There is all the answers I gave, they are not general. Everything has to be modulated by your application. So if you go to classification of the terrain on the tropics, with optical I can have one image every 3 months. Tones of white. We were doing some monitoring of floods in Southeast Asia, and I don't want to lie, but we had terabytes of clouds, white, everything white. So we switched it to SAR, and then SAR is more than perfect. That depends on your application.
Thank you.
Carlos, I will ask you a question.
Okay.
So one of the excellent byproducts from most of these images is digital elevation model.
This?
Digital elevation model.
Digital elevation model.
DEMs, popularly known. But unfortunately, the DEMs that are derived from various different image sources for a same region are not equal. Is there any study that leads to a kind of a statement that the DEMs that are derived from various different mechanisms is the same?
I mean, I don't want to say that there are no studies. For sure, someone should have tested, because now everything is tested nowadays. But this is true. I mean, that depends on your, especially on your frequency. Okay. So, for instance, you have TerraSAR, which has derived a
Tandem X, yeah.
and the digital elevation model.
Elevation.
A different thing is a digital surface model, which is different. Okay, so that depends. I mean, I don't have a clear answer. I mean, for sure, I think that the higher the frequency, the closer you are to the top of the canopies, the lower the frequency you are at the top. But an accurate idea of how close, how far, this I don't know, because I'm not expert on interferometry.
Yeah, that's
maybe
what
BIOMASS will give some light into that, because it's very low. The problem with P-band is that you will penetrate into the ground. So there is not also a digital surface model, because you can penetrate.
Yeah, actually I don't want any of the features that have been appearing because of anthropogenic activity. I want just the, the elevation value of the ground from the mean sea level. And not all DEMs are accurate enough. And so that is where I still say that billions of dollars have been spent on generation of DEMs. And they have been useful in mostly, hydrological studies, modeling studies.
Yeah, I agree.
But if I want to have a subtle morphological changes, I want to take the advantage of those things. If I want to really model a kind of sand dune behavioral pattern, and I want every small detail in it, and that's where I still rely on topographic map-based DEMs.
Let's wait for LiDAR systems, for instance.
Yeah, LiDAR systems.
LiDAR system may give some clarity into that. But whenever the surfaces are bare, I think more or less, most of them are equal.
Yeah.
The problem comes when you have vegetation.
Yeah.
Even with LiDAR, you have JEDI has a lot of problems on vegetation.
Thank you, Dr. Carlos, for your session. Now it's my great honor to welcome you to this special session where we have the privilege of meeting the President of IEEE Geoscience and Remote Sensing Society for the year 2023, Dr. Mariko Burgin. Dr. Mariko is no stranger to IEEE GRSS community, having served as the Executive Vice President for the preceding term from 2021 to 22. Her commitment to advancing the field of geoscience and remote sensing is evident in her continuous dedication and contributions to the society. Currently a member of Administrative Committee and IEEE Senior Member, Dr. Mariko brings a wealth of experience and expertise to her role. Her professional journey is deeply rooted in systems engineering and mission formulation, particularly in the realm of advanced technology development for NASA missions. Notably, she plays a pivotal role in supporting the Mars Sample Return Initiative, serving as the break-the-chain domain lead. In this capacity, she acts as a capture lead, facilitator, and systems engineer in project system engineering plus formulation. With over 10 years of governmental and academic experience, Dr. Mariko has been at the forefront of developing geospatial solutions for Earth and leading research and development teams for missions extending to Mars and beyond. Her technical prowess lies in applied electromagnetics, where she specializes in modeling and simulation, as well as algorithm development. Her expertise extends to active and passive microwave remote sensing, encompassing the radars and radiometers. Her interests are diverse, ranging from the application of machine learning, feature extraction, computer vision, to data fusion of multitemporal data for Earth observation. Her impressive list of accomplishments include being the 3-time recipient of JPL Team Awards, 2-time NASA Group Achievement Award, JPL Discovery Award, and JPL Voyager Award. Additionally, she has been recognized by the IEEE for her outstanding contribution to promoting women in engineering. Beyond her research and accolades, Dr. Burgin has actively contributed to growth and development of future generations in the field. She has advised and mentored numerous graduate students, postdocs, and interns, shaping the next wave of leaders in geoscience and remote sensing. Please join me in extending a warm welcome to Dr. Mariko.
Thank you so much for the kind introduction. I really appreciate that. Thanks also for taking the time to listen to me. I know this is a hard act to follow here. I will have less technical detail, but I'm really pleased to be here as the IEEE GRSS President, and I can build the bridge from this talk, which was a Distinguished Lecturer talk, to INGRSS. And I'm going to talk to you a little bit more about GRSS and what it is, and I'll hope to address the diverse audience. I know we have distinguished lecturers, we have ADCOM members, we have volunteers, we have chapter chairs, so some people know a lot about GRSS, some people might know less, so I'll try to hit the highlights for everybody. Actually, I didn't want to present too long. I really wanted to just give you a few highlights, and then I hope you come and talk to me. I'm here until Monday, especially today and tomorrow. I'm really here to meet the community, and I think that's my most important role, and I get to talk about what other people do, and so this is really my honor as the Society President. I'm the Society President for this and next year. Here's my email address. Feel free to reach out to me anytime. I'm always happy to hear from people. Sorry if I'm standing in your line of view. I just wanted to briefly talk about GRSS. We are truly a global community. We were founded in 1961. Still going strong is what I call it. We're one of 39 IEEE technical societies, and you can read here what our scope is. Really fostering engagement. I think that's really the most important thing as it relates to geoscience and remote sensing. You heard me say ADCOM. ADCOM is the administrative committee at the society level. That's basically the board of governors who leads the society. The president is one of them. And then the scope you're mostly familiar with. We just had an excellent presentation on theory, concepts, and techniques, right? This is really why many of our members are part of our society. Currently, we have about 5,700 members in 144 countries. And most importantly, we're organized into chapters. And chapters are really, I think, the heartbeat of our society. I had the pleasure of attending a chapter chair meeting this morning. And it's really amazing to see, like around the world, we have chapters, we have student chapters, we have ambassadors. And this is really a way for the local community to contribute and join. An eye chart about membership, which I think is very important. You can see here the dark blue line is sort of how we're doing this year. This is from up to October, our distribution. In summary, our society as compared to others is academic. We have some industry and government. Government is also strong. Industry we're still working with. Carlos talked about new space. I think that's one of the challenges that we are facing right now. The field of geoscience and remote sensing is changing. Academia, government, and industry, there's a lot to bridge and to encompass. And so if you have thoughts on how best to do that, I want to hear it, because this is really something I think we're going to face for our publications, for our conferences, and so on. Another thing is I'm looking also during my presidency at our diversity statistics. Below, I'm talking about gender, but it's also about geography, distribution of our members around the world, seniority. I think these are all statistics that we're starting to collect and that IEEE is also very interested in nowadays, which I'm really happy about, because it starts at IEEE level and it's coming down to the technical societies. To be honest, we need more diversity in our society, and there's some initiatives that we're currently running to improve that. This is my plug here. If you're not a senior member yet and you've been in GRSS, please apply. I'm happy to be a reference if needed. You don't need a lot of references to do so. It really is the first step from being a regular member, becoming senior member, and then you're open to becoming a fellow at some point, which I hope everybody should achieve at some point. This one is really the eye chart, our publications. I mean, we have 4 refereed publications. These are unfortunately only the acronyms, but we have TGARS, GRSL, JSTARS, and GRSM. You see them here at the bottom row. Then we also have 2 co-sponsored journals, BIOMASS, you see it up top here, and Transactions on Radar Systems, and new since 2023, GRS section in IEEE Access, which is at the bottom, the top right. There's a lot going on. There are lots of editor-in-chiefs, there are lots of associate editors, there's lots of reviewers. Publications by itself is a very deep and interesting topic. Also publications, the philosophy around publications is going through a lot of changes for our society, but also for IEEE. We're very thankful for everybody who reviews. It is really a service to the community, because I know you do it, many of them do it on their own time. And so this is something also, if you have more thoughts, and I'd be happy to hear. One thing I wanted to point out, we have an e-newsletter. If you're new to GRSS or are not familiar as of yet, sign up for it. It's sort of a monthly free newsletter delivered to your email, and you get a very good overview of what we're doing, what the upcoming conferences are, job opportunities. It's a really interesting read. Then technical committees. We have technical activities across our whole society. We have 8 of them. It's really amazing to see how diverse they are. They go from earth science informatics, frequency allocation, instrumentation, future technologies. You pick and choose standards, or even our newest one, which is remote sensing, environment analysis, and climate technologies. So technical committees are really most of the time the starting point. You find a technical committee that you are interested in. They have their own e-newsletter. They have their own initiatives. You can sign up, you get involved. Some people then become chair. This is a really good way if you're really interested in your specific field. And they do some really interesting things too, because, for example, one of our technical committees joined forces with another initiative, and they built this CubeSat program. Or we have data fusion contests, all sorts of things. There's also a very interesting podcast that we have. It's called Down to Earth, which talks about our technical committees, but also a variety of other topics. That one is very interesting to follow as well. Then, bridging, networking, connections. Those are our conferences. You see here in 2023, we had our big flagship conference in Pasadena. I actually live just around the corner in Los Angeles, so it was next door. We had a lot of abstract submissions, a lot of registrations, and in the end, quite a few papers. We were really happy that after COVID, things started to recover. We're looking towards having flagships now, flagship conferences in the next years in Athens and in Brisbane. Then, of course, we're all here because of INGARS, and we're really excited for that as well. It's one of our regional symposia. We also have other ones in the Mediterranean and Middle East, and then also in Latin America. So something to look forward to in different regions. And then this is a long list, which I don't want to really go into detail, but we don't often talk about. Specialty conferences. So GRSS also co-sponsors conferences, and there are actually quite a few of them. And I think this is something too, as I look towards the second year of my presidency, to give it more highlight, because we always talk about our flagship conferences, but there's a lot going on in different cross-sectional areas as well, with other societies, with other communities. Then I think I have 2 more slides. One is about professional activities. That's really where our distinguished lecturers, our young professionals, and our idea committees live. And just to give you brief highlights over these, distinguished lecturers, you know, Carlos is one. There's, I think over there sits another one. There's several. Like, distinguished lecturers are really selected speakers who the chapters can ask to travel and visit them. I think they're an excellent resource, and they're sort of our representation to come. I hope we can increase the program over the next few years as well to offer more diverse topics. We have both academic and industry distinguished lecturers, which I think is also an excellent next step. Young professionals exists at the IEEE level, and we've sort of adopted it into our society. They do excellent mixers. They have an Earth at Risk image contest. They're very, very active. They have very interesting, graphics and ideas. So something also to follow. If you're at the chapter level and you're looking for ideas or ways to get engaged, that team always has needs for new people and really organizes fun events, I have to say. And then IDEA, which is Inspire, Develop, Empower, and Advance, is our committee that really looks towards diversity, looks towards giving opportunity to everybody. And for example, we have a $500 professional development microgrant. We have a Women Mentoring Women program, which I highly recommend as well. I'm part of it, and I think both as a mentee and as a mentor, this Women Mentoring Women program is I highly recommend. So if you have any questions, please feel free to talk to me. And of course, much, much more. And I think this one is the last portfolio I wanted to talk about, which is, I call it the learning and other opportunities. GRSS really is tied into IEEE education, and there's a lot going on there as well. We have GRSS schools. We have lots of webinars that are going on, both from our TCs, but also like organized by the community. We have programs for high school and undergrad student outreach. And very new, we have now student grant challenges, which we have the 4th iteration going on right now. And we also give out travel grants. There's a slight change there as well. It used to be just travel grants for our flagship conference, but now, for example, INGARS is also making use of that. So I'm really happy about that as well, to encourage more students and people to attend our conferences. And then a pointer I always like to add is to this Coursera course that we have, which has already had more than 12,000 learners, which really blows me out of the water. But I think this is another thing that we need to explore, like how do we disseminate this information, not just on IEEE channels, but also to our chapters and to in the end, to the members who want to learn and educate themselves. The next 3 slides I'm going to step over because I want to stay within time, but this is basically the org chart of the AdCom. If you have questions, feel free to talk to me about it. Otherwise, I'm just going to move on. This one here would be an interesting chart to talk about because in the first year, I started an ad hoc committee on diversity, equity, inclusion, accessibility, and belonging. I really put the longest acronym in there that I could. But it's sort of an opportunity to really look at different transactions of our society, look about accessibility and belonging, and I'm happy to talk to anybody who wants to hear more about this. And then finally, this is just sort of an eye chart for me. I'm very interested in not just the geoscience and remote sensing community, but also our sister societies, not just within IEEE, which this chart focuses on, but also others. And so for next year, I already have some plans to expand this and to grow bigger, because in the end, I think it's all about cross-community communication as well, more so than before, I think, because the fields are overlapping and really the fun stuff happens in the intersection of it when you can compare notes and do new things. All right, so this is the last few charts, but I just wanted to say really what lies close to my heart is really that I think GRSS should be your professional home. I think it always starts with technical excellence, so I'm glad I am following a distinguished lecturer talk because I think that's the important stuff. But then I also want to have a society where everybody feels welcome and belongs. That's very important to me too. And then finally, I think it should be a society where you can also shape it, because I think once you volunteer, once you become part of it, that's when you really get involved and you feel strongly about it. And I think that's also a reason why I became involved in GRSS, because I like to organize events and bring people together and have these discussions, especially about SAR, which is also my background. So, and this is one thing, it's a starting point. Like, we're really thinking about the value proposition that GRSS can bring to you. These are some points that you can think of, but we're trying to polish this a little bit more and think about it. Why do you attend our conferences? Why do you publish in our journals? Why do you want to be part of a community, and how can we help you? Because in the end, it's all about the community building, I think, that these technical societies need to do. Yeah, and with that, I just wanted to say here's a quick plug for if you're not a member yet, feel free to become one. If you need help with the weird structure that we have between preferred and essential, let me know. But you're here for INGARS, and I'm really happy that I got the chance to talk to you. And as said, pull me aside. I'd be happy to hear your perspective on our society. Thank you so much.
Thank you, ma'am, for your talk about the GRSS community and the events and the opportunities which we have. Now I would like to call Dr. Jayashree Nair for giving a concluding remarks for this session.
Thank you so much for being here. But yeah, I have to say that Mariko did say she wanted an interactive session. So we are still open for some questions. Do we have any questions for the president? We don't get to meet the president that often in person. So let's make the best of this opportunity. Any questions? Yes. Definitely, yeah. Third time. Yeah. Thank you so much for coming. And yeah, so I think from the GRSS Bangalore chapter, we do have a pending question for you. So we have been trying quite a bit to increase the industry participation in this chapter. And in the last couple of years, we have been slightly successful. So we do see a lot of industry participants here. So do you have any ideas on how we can improve on this?
Well, I mean, industry participation is really the difficult one, especially because of new space and the value proposition to bring. We do have a director of industry relations who's really thinking about this now. So one thing I could do is connect you with him, and because we're basically setting up a working group right now, and one thing that he's trying to do, his name is Nathan Longbottom, is try to figure out what does industry want. Because one thing that we've noticed, for example, in the United States is they organize their own meetings. They don't really use IEEE or anything anymore. They just make their own community-driven events. The publication scheme is completely different as well. So it's really puzzling to figure out how can you engage them, right? So I said, why don't we ask them? Like, what do you actually, where can we help you? Because I think that's the thing. Like, once we understand what they like, then we can help. So I don't really have a good answer for you, unfortunately. But you're right on the spot with the question.
Thank you so much. Yeah, we do have a few. Yeah, you would like to ask.
I think since you both mentioned I'm from industry and Professor Jam actually brought me into this, so this is great. I represent SATSHA here. But I think in terms of what industry want, I can just talk on my behalf. I had a research and development team at the company. Sometimes we have this challenging question for which we are trying our heads against the wall, where we know somewhere somebody has done like 20 years worth of research and they know the answers, right? And instead of us, going and looking and mining for that data, if there are these chapters where, professors are involved and, people who have a 30,000 view of the things, along with the industry, that will actually propel all of us together, is what my view has been. And I've been bouncing my ideas with ma'am and other people also around this area. But this is one thing I think could start as a local chapter.
Thank you so much, Divya. Any other questions? Research? Yeah, please.
Hello. So I'd like to thank the IEEE Indian for the section for organizing the webinar. So basically, I'm from an oil and gas sector. I'm a pipeline engineer who got into SAR, and our team really loves SAR right now. And those webinars which were organized by the team is really helpful. So I would think one of the things would be capacity building. So a lot of people don't know about remote sensing. They find satellites something scary that's not there, like not useful for them. But once we're in there, we find like satellite is very accessible. It's there and it can solve the ground problems. So capacity building would be something you could look at.
Okay.
In whole of IEEE GRSS in its history, I believe we have only 2 women GRSS presidents. First one being Melba Crawford, and the second one is Dr. Mariko Burgin. So Melba Crawford visited 2014 to Jodhpur chapter and in between no other presidents have visited, so she is the next one. We need more women GRSS presidents. Yes.
Well put. I think factually, actually, there were 3. I also realized that there was one more female president before Melba, but very way back. I've never met her, so, but yeah, I'm happy to follow in their footsteps, and yeah, I'm very happy to be here, so thanks for having me. Thank you so much. Thank you. Thank you. Oh.
So with that, we'd like to conclude the session. Thank you all for being here. There's tea served outside, and we can continue networking session outside. Yeah, thank you all.